Hello everyone. So in my last two lectures, I have given thorough details about the gravity methods. Now in this lecture, I will be talking about the gravity anomalies from a bodies with simple geometry. So what are those bodies? These bodies are like sphere, semi-infinite slab and horizontal cylinder, and this is one of the formulas of the sphere, gravity anomalies from a sphere. So we will be deriving it with the basic physical and mathematical funda, no more extra in it, and you will find it very interesting how the bodies within the subsurface of the earth or inside the surface can give rise to different anomalies, and how physically and mathematically we can interpret it. And last we'll talk about something about the anomalies, means what type of anomalies are there in a broader sense, and there will be an ambiguity in anomaly. So let's start from our first slide with the sphere of gravity anomaly. So you can see there is a surface of the earth and there will be a sphere buried within the surface. So what are the terms? First let's see what is there is an delta m. Delta m means mass excess or deficit. Suppose there is a body, and within the host rock which is having higher density, host rock is having higher density than the body, then it will create a deficit of mass. Otherwise, if the body is having higher density than the host rock, then it will create a mass excess, and there will be a volume density of the sphere, and the delta, the gravitational attraction of the acceleration of the sphere is there. The change in the gravitational acceleration, which can be denoted as, we have read in our last lecture, gm by r square, where delta m can be written as the density multiplied by the volume. The volume of the sphere is like simple mathematics, 4 by 3 pi r cube. Okay. Now you substitute that delta m, that is delta rho into v, within that formula with the Pythagoras theorem within this triangle, that's x square is equal to r square plus z square. The gravitational formula will be delta g, that reduces to that formula with the dependence on the distance, vertical distance and the horizontal distance. Z is the vertical distance of the center of the sphere from the surface of the earth. Now, but in actual case, what we measure? We actually measure the gravitational attraction only the vertical component, because this picture, this has been illustrated in this picture. You can see there is the delta g, that means the gravitational attraction in this direction. It makes an angle theta with the horizontal surface. So this delta gx component will be delta g into cos theta, but our gravimeter measures only the vertical component, which is delta g sin theta. So we have to calculate for the gravitational attraction of the buried sphere, we have to calculate the delta zz component, that means delta g into cos theta. So where r, here r is the radius of the sphere that I have already discussed, and delta rho is the difference in density, that's same as the delta m. There is a vector sign, this is a vector formula, delta g, delta x plus delta gz. So if we just substitute these values, what will get? Delta zz, it is dependent on the radius of the sphere, the density difference and the vertical and the horizontal distance. This z is the vertical distance and x is the horizontal distance from the observation point to a point directly above the center, portrayed in my last slide. Now with some mathematical calculations, that delta gz reduces to that 4 by 3 pi rg delta rho r cube by z square into that additional term. Now this term is like very important. This is the gravitational central peak value, means at x is equal to 0, this value, it gives the value at the center of the sphere, that within the center of the sphere. Okay, so this gives the maximum value of the gravitational attraction, and with the term and this term, if this term increases, this reduces the gravitational attraction. Okay, so this is our central peak value, this is called. Now you can see the graph, that means we in a practical cases we have to encounter with this type of graphs. So by seeing that graph we can evaluate the, okay, this is coming from the sphere, but the broader picture is not that so easy, but at a glance you can see the shape of the anomaly, so that you have an idea that yes, this type of anomaly is coming from a sphere. You can see there is a bodied sphere A and this sphere is B. So for A, that is very too much of sharp figure, and for B that is broader. Okay, so let's see that. More deeply buried, that means B is flatter and broader anomaly, and it's a shallow depth means A compared to B, that is our sharp anomaly. Okay, so for sharp anomaly this is that, but why this? Because it can be interpreted from this term. For the sphere is with the sphere is more deeply buried, that means Z is less, that term decreases less rapidly compared to the term which is on the sphere, that means the sphere at a shallower depth. So for the sphere at a shallower depth, the Z value is less than that of B. So for Z value is less, that term decreases, that delta ZZ terms decreases more rapidly. Okay, and for the, you can see that this amplitude is dependent, this central amplitude peak value at x is equal to 0, that x is equal to 0, this peak value is dependent on delta G0, that means it is dependent on the radius of the sphere. So more the radius of the sphere, more the density difference, I mean mass anomaly is by mass excess, delta rho is directly connected to mass excess, the more will be the amplitude of the anomaly of the sphere. And for so for A, this amplitude of the anomaly is more because the Z is less. For B, the amplitude of the anomaly is less, but it will be more broader than A. And by measuring the width, width of the anomaly, we can find that this is the half amplitude width. That means the width of the anomaly where amplitude is half the maximum amplitude here. So it is connected to Z by the formula Z is equal to 0.652 into W. So we will be given with the information of W. From that we can get the depth approximate at which the sphere is buried. So this is a vector formula, delta GZ is making an angle theta in my last slide, and we are measuring only delta GZ. So this is whole of the formula of the sphere, buried sphere, and which is portrayed by a graph, this graph. Okay, now next to see different aspects of sphere, how it is, the buried sphere is deeply or shallowly buried. Let's see. Now this is the formula, that means delta rho is positive, that means delta GZ is positive, delta rho is negative, that means delta ZZ is negative. So mass excess causes the increase in gravity, and mass opposite case happens for minus delta rho. Now second case, what happens if the sphere is more massive, that means delta rho is large, what we can see from our amplitude anomaly central peak value, the greater will be the amplitude of ZZ. For less delta rho or delta R, the amplitude of ZZ will be less. Okay, so this more the, obviously we can intuitively we can think that if the sphere, this bigger sphere, the amplitude of the anomaly will be more. And the third case, that is also described in the shallower, this is very important. If the sphere is more shallower depth, then the amplitude will be more sharp. It can be called as residual type anomaly, which I will discuss later. And for deep, that is the regional anomaly type, that will be the picture will be the more broader and smoother. Okay, so any anomaly coming, so if we can see any anomaly that is more broader and smoother, we can think of it as coming from the more depth compared to it as a shallow depth. Okay, next I will be moving to gravity anomalies due to the slab, semi-infinite slab. In a practical cases, it is very important. It is also, so not going into detailed derivation, I will just giving the formula according to the semi-infinite slab. At one axis, it is going to the infinity. So it is at a, from the earth surface, it is at a vertical distance Z, the central plate, thickness delta H, delta rho same as the density contrast with the host rock, and it is making an angle phi with the station with the horizontal line, this line. So according to them, that anomaly can be modeled as, can you remember these things of formula? Can you think of that? In my last lecture, it is something like a Booger slab correction, where given that station can be, if the station is at a height h, it can be replaced as a block with density anomalies and that thing with the same formula, and this angle is can be written as pi by 2 plus tan inverse x, that x distance, this distance is x by that z distance. So there are different aspects with that, the delta gz can be written as with that formula. Now for infinite, that if for an infinite horizontal sheet, that is same as the Booger plate correction that I have already told, the 2g delta rho delta h it is same as the Booger plate correction. So now we will see what in what aspect this is very important. Actually this is the model of a fault, vertical fault. The thing fault I have not discussed in my previous lecture, it is a geological thing. For tensional and the compressional force, there will be relative displacement between the two blocks, for which is the responsible for the earthquake things. It is very important in the geological aspects and also in the geophysical aspects. So if there is a fault plane and h is distance, and there will be relative displacement between the two blocks, and that fault plane, that faulted block can be modeled by a semi-infinite slab, and we will see now the graph of that, the gravity anomaly for this faulted block. By seeing that gravity anomaly, we can interpret, yes, there is in many mineral aspects and geophysical aspects, this fault plane, finding of fault plane and visualization of the fault plane is very necessary and very important. So afterwards in my sum up slide, I will give detailed discussion about the fault plane, what is the fault, what is the different type of fault, what role it plays in the geological and geophysical aspects. Now you can see that the semi-infinite slab extending at infinity in this direction with the density contrast delta rho, and there is a profile of that gravity anomaly with delta z at the y axis along with the depth. Now it is the edge of the slab, and here is the x direction. For x tends to infinity, minus infinity, that means here where there is no such slabs, the gravity anomaly is 0, it is obvious. Next we move to that case for x is equal to 0. For x is equal to 0, that is over the edge of the slab, the gravity anomaly is half of the Booger slab correction. And when x is equal to infinity, that I have discussed in previous slide, there will be a full Booger slab correction. The Booger plate correction will be available for the just over the slab, and at the edge of the slab, that is a transition point, that will be half of the Booger gravity anomaly. So that is the faulted model of the semi-infinite slab. Now the same thing for the sphere also happens. If there is a delta rho, this is mode, and there is a shallow and deep body. In the shallow body, that means the semi-infinite slab, the gradient will be steep, and the amplitude of the anomaly, that amplitude will be dependent upon the value of delta rho cross delta h, same as that of sphere. Delta for sphere, that delta h was that the radius of the sphere, and that there will be a delta rho for also for the sphere. So more the delta rho delta h, more will be the amplitude of the anomaly. And if the gradient is, if the body is at larger distance, that will larger depth, the gradient will be more smoother, and if compared to the body at shallower depth, so that is very sharp anomaly. So that can be, the more deeply buried is a gentle gradient, and shallow depth we are having sharp gradient. And more deeply buried means that we can, from the anomaly we can call it as a regional anomaly, that I will discuss in afterwards. Shallower depth is a residual anomaly, that will give sharp gradient for any type of body. Only the profile will change, but the basic things about the bodies, that means the dimension, if the dimension of the bodies are large, we will be having more anomaly amplitude, and if it is more deeply buried, there will be smoother and anomaly and gentle anomaly, and shallower body we have a sharp anomaly. Now we move to the horizontal cylinder. So the derivation can be done by thinking of it as a single line element parallel to the axis and integrating over the polar coordinates. But for the time being, now I am giving the only amplitude of the anomaly, same as that of the sphere, only that central peak amplitude is different. And with the term for sphere, you can remember that there will be a 3/2 power. Here there is no power. So for x is equal to 0, we are having this term. This is called the central peak value. So the gravity anomaly resembles to that of the sphere. Here the gravity anomaly, and there is a half amplitude width, there is a half height width, where z is equal to, we can find that depth at which the horizontal cylinder is buried, it will be related to the w, half height width, at 0.5 into w. From that we can estimate the depth of the body. Now the most important point is that the laterally that the anomaly decreases less rapidly, because that term is here the linear term, and for sphere that is dependent as 1 this to the power 3/2. So obviously that term decreases in the x direction, positive or negative, because the profile is symmetrical less rapidly than that of the sphere. Otherwise, so if you are having two profiles with the same shape, then the lateral decrement, that means the x axis, if that is sharp, that will be sharp for the sphere, and that will be less sharp for the cylinder, horizontal cylinder. So in that way we can discriminate the profiles between cylinder and the horizontal sphere. I hope you are clear about that. And if that the sphere is buried at a more depth, then the profile will be more gentle and more smoother, and if it is within the shallower depth, then it will be very sharp gradient anomaly. The same, that will be same for any type of bodies. So now the most important thing is the gravity interpretation, or you can find it in the magnetic also, that means the ambiguity. So a given, suppose we are having a particular profile, this anomaly, anything potential field distribution, that profile can be explained by a variety of mass distribution. So at a shallower depth, if we are having that type of body extent, then more deeper we are having a more density and more radius. So it will give that combination, that three combination will give the same gravity profile, and that will give also the same negative gravity anomaly. So that is called the ambiguity in the geophysical interpretation. So we have to be thorough knowledge, and we have to be thorough knowledge about the regional and the residual anomaly, how they behave, how the profile looks like. But due to the ambiguity, what is our duty? So we have to assign a regular shape to the causative body for the simple modeling, and we have to assume that the model has uniform or uniformly varying density contrast. So if there is any body with a complicated shape, as per our basic needs, we can give it a regular shape to which the gravity modeling is known, and we can accordingly find the gravity anomaly profile, and we can model it. So it is our basic idea, and this is called the gravity ambiguity. So due to this ambiguity, it is believe me, it is extremely tough to identify which type of body is there within the subsurface. In that case, geophysics plays a huge role, and to have a clear idea of the ambiguity, we need to know about the anomalies, means regional and residual. What do you mean by regional? Simply, if there is a gravity field, it record anything anomaly. So it is a cumulative source of shallower and deeper bodies. The two types of bodies are there. Next is that regional anomaly. It is a long wavelength anomaly, because it is coming from a deeper source, and it exhibits broad and uniform variation. That I have already exhibited in my previous slide for sphere, semi-infinite slabs, and also uniform and horizontal cylinder, the deep-seated origin. Now the short wavelength anomalies, or it is called the local field anomalies, or the higher frequency anomalies, that is associated with the shallow features, and it is a very sharp anomaly, higher frequency, shallow. It comes from the shallower depth and with high curvature it is having, and with a relatively shallower origin, so with a noisy feature. Now, so in practical we are having two types of anomaly, that is one broad anomaly and smoother long wavelength, and is a short wavelength higher frequency shallow features of anomaly. As these two are both important, if you need to know about the ore bodies of interest or very shallower features, in that case you have to remove the long wavelength regional features from that anomaly, and you have get rid of that long wavelength anomaly, and if you subtract it from the original anomaly, then you can get the residual or the shallower source anomaly. So the original anomaly subtracted from the residual regional anomaly will give rise to the shallower depth bodies. So it is the so I hope you have gained an idea about what are the gravity anomalies from different bodies and what type of anomalies are there, and what makes it so difficult for any geophysicist to interpret what types of bodies are there. It needs thorough mathematical and physical and also geological knowledge. So little bit geology with physics can make us more knowledgeable or make us more efficient to interpret about the geophysical signatures. So now, this type, so in my next lecture I will be giving some light on the numerical problems on the gravity, that will find it extremely helpful for intermediate students or for BSc physics students and for also for MSc students. Thank you very much, and if you really benefit from my channel or like it, please share, subscribe and share it to your near ones and dear ones, so that they can also get benefited and for also getting more updates. Thank you.